Hi, everyone. I think we're going to go ahead and get started now. So if you get settled in your seats. My name's Erin Hennessy. I am co-chair of the seminar series with my colleague, Dr. Chris Peters. I have the pleasure of announcing our speaker for today, Dr. Trenton Smith, all the way here from the University of Otago in New Zealand. I figured out how to pronounce that correctly. Dr. Smith is an associate professor at the university, and his work applies economic methods in biological perspective to better understand behavioral phenomenon. He's been particularly focused on dietary choice, obesity, food addiction, and other really interesting topics. In looking at his background, I came across that he's chosen to pursue his education, training, and career in very beautiful locations. So I'm not sure if those two things are combined. But starting off at Stanford, having backgrounds in as dispersed as biology and economics and engineering. I also just found out one small fun fact, that he was a teammate of our dean on the wrestling team at Stanford. So we had the pleasure of having Dr. Smith a number of years ago and are excited to have him back. His work has been featured in prominent journals such as The Lancet, and I was pleased to find out that we were also 1 degree removed from a colleague that we both have, Dr. Ross Hammond at the Brookings Institution. So while he holds his professorship at the university in New Zealand and we are here in Boston, we are very, very connected. So I hope you can all join me in welcoming Dr. Smith to our seminar series.
Thanks, Erin. Okay. All right, so I have a lot of ground to cover here, both in terms, well, maybe not in terms of slides, but in terms of disciplines. So I want to tell you, I'm going to start by so I'm going to give you some, I'm going to show you some results, some unpublished results so you could think of these as preliminary results from an experiment we did. But first, I want to talk a little bit about the background and how I came to this. So, so a few years ago, I wrote so in 2011, I published this paper in the Journal of Food Policy, and in this paper was very ambitious. We attempted in this paper to lay out the history of the past century plus of the American diet. Right? And so we and sort of our method in this paper was to look at the history and look at it in terms of both the history of food processing, the history of nutrition science, and the history of public policy around sort of public health nutrition. And so after reading this history from the perspective of an economist, we thought we saw a pattern, and we argued that it was this, that you sort of originally you have a food processing innovation come along, it's introduced, it's widely adopted, it's usually introduced for purposes of industrial efficiencies, right? You process foods in a way that makes them easier to transport and distribute to a large market. So the innovation's introduced and widely adopted. After sometimes many decades, nutrition scientists figure out, oh, there's a side effect of this processing technology. It's now killing people by the thousands or hundreds of thousands. And then once that's fairly well settled, it basically sets up a political fight, right? So by the time the science is settled on, oh, this processing technology is killing us, there's now this entrenched industry interest, right? That doesn't want to reformulate because they have all all this investment in the current formulation. And so that typically takes a decade or more for that political battle to work itself out. And so just to give a specific example, you could think of trans fats. So Crisco was introduced, I think, in 1913, something like this. Crisco is very partially hydrogenated vegetable oil. So you heat up a vegetable oil in the absence of oxygen. You probably all know this. It partially hydrogenates the vegetable oil. That makes it solid at room temperature. It makes it more stable, so it doesn't go rancid quickly. So you can bake it into baked goods, ship them across the country, and not have to worry about shelf life as much as you would if you're using natural oils. And so that was 1913. Crisco had this big campaign. I think the theme, the slogan they used was, in addition to actually having to teach, American housewives how to make pies with this stuff, they literally gave away cookbooks teaching people how to do this. They also promoted it as actually being healthier than those, than those animal fats, right? So it's more hygienic, it's more digestible was their big slogan. Crisco's more digestible. So anyway, they succeeded in converting the American diet to this consumption of partially hydrogenated vegetable oils. It wasn't until, well, the 1980s, more or less, that the chemists figured out, oh, this hydrogenation process creates trans fats. I have this vivid memory as an undergraduate, in my undergraduate organic chemistry class, of my lecturer writing the structure for the trans fats molecule up on the board and pointing at it and saying, this more or less doesn't exist in nature, but it's in almost everything we eat, right? You should worry about this. So this is in the late 1980s. By the early 90s, the epidemiology was fairly solid on trans fats are killing people and giving us heart disease. And then it wasn't until 2006, I think, that the U.S. introduced the mandatory food label, right? And so that's more than a decade, right? So from sort of 1990 to 2006, you had this period in which, the experts and definitely the industry more or less knew that there was this defect in this product, and yet there was this political battle over what we should do about it. The economic solution to that is pretty simple, right? So let's see, so you're mostly not economists, so I should quickly explain the economic theory behind this. So in 1970, George Akerlof published this classic paper called The Market for Lemons. And what his paper was about, well, the example he used was the used car market. So the problem with used car markets is that some of the cars for sale are lemons, right? So there might be some good used cars for sale, but there are also some lemons, right? Cars that are likely to break down. And the seller of the car knows whether my car is a good car or a lemon, but the buyer, on the other hand, can't tell, right? And they don't necessarily trust what the seller is telling them. And so that potentially introduces this dynamic whereby the sellers of good quality cars choose not to introduce their car to the market. I'm not going to sell my car because I won't be able to get a good price for it because the buyer is all suspect it's a lemon. And so you can get this dynamic where essentially all the good cars get eliminated and there's nothing but lemons for sale on the market. So in economics, we call this the lemons equilibrium, right? And it's a form of market failure, right? It's a market breakdown. You have there's a missing market for high quality goods that could exist if not for this information problem, this hidden quality problem. And so that's what I mean when I say market failure. So I argue in this 2011 paper that this stage 3 in this process you should think of as being a pretty clear-cut lemons equilibrium problem, right? So it's the processed foods are like used cars. That's the message from that paper. And there are many. It's not just trans fats. There are a lot of examples of this. Trans fats is one of the happier endings, right? So even though it's true that there was all this heart disease for 100 years, nearly 100 years from this defective product, in the end, all it took was a simple label, right? And that's what the economic theory says. When you have a hidden quality problem, what you need to solve it is a credible third-party quality verification system, right? Food labels. So this is the main justification for having mandatory food labels, is to solve lemons problems, solve hidden quality problems. Okay, so this is the background that I'm bringing to this paper, and even in this 2011 paper, one of the things that I wrote about, towards the end of the paper, when we ask, is this still true today, right? Do we still have a hidden quality problem today, or have they all been solved? Glycemic effects is one of the things that I wrote about in that paper, that this is something that consumers can't easily tell from a food label, and it has a major implications for public health. And so it likely represents an important market failure. Okay, what's a little bit different and I think fascinating about blood sugar effects is that there's at least some intriguing evidence that rather than just being sort of an innocent, unintended consequence of food processing, that that has no effect on consumers, right? They can't taste it. They just have these health effects in the long run. It's possible that that blood sugar effects themselves are fundamental determinants of demand, right? So it might be that the blood sugar dynamic that a processed food gives you is part of what makes it addictive, right? Part of what makes you buy it again in the future. So that makes this, it makes blood sugar effects a little more, maybe possibly a little less innocent than these historical examples we talked about, where it's just an unintended side effect with no effects on demand. Okay, so you all know what I mean when I say glycemic response. So you eat a carbohydrate meal, it makes your blood sugar shoot up. Your pancreas responds by secreting insulin, which has the effects of making your blood sugar come back down. But that process, if your meal is large enough, that process can take hours, right? So it's not. So there's a lot of room for variation, I guess. When I use the word dynamics, that's what I'm talking about, right? So there's this dynamic response to a carbohydrate meal, and the dynamics can look a lot different from one meal to the other, and a big determinant of that seems to be processing. So there's this famous Granfeld 1991 paper where they did a laboratory experiment where they fed human subjects in the laboratory either spaghetti or white bread, and they showed that the white bread had this dramatic effect on blood sugar, right? Massive increase in blood sugar, massive decrease, to the point where you're below baseline, right? So this can have behavioral implications, right? So after the meal, once your blood sugar shoots down below baseline, you can have sugar cravings, right? So interesting behavioral implications. And the cool thing about the Granfeld paper was that the white bread and the spaghetti they were using, one was high glycemic and one not, they were made from the same ingredients, right? The laboratory technicians literally made it from the same ingredients. So it was the processing that created these differences they were observing. Okay, another important thing about blood sugar response is that it's mostly imperceptible to the consumer. That's why you see diabetics go around all day pricking their fingers and taking blood samples. Even if you know a lot about this, it's not easy to tell just by how you feel what your blood sugar happens to be at any given moment. Okay, and so this is the behavioral conjecture I'm going to offer. And this is something that when I talk to my psychologist friends about this, they'll say, well, of course, glycemic effects make foods addictive, right? And they'll list off all these effects, right? And here they are, dose, rate of absorption, tolerance, craving, withdrawal. You can sort of find all these things with blood sugar response. Okay, so that's a behavioral conjecture. We're going to use it in you'll see we use it in the way we design our study. It turns out in the end, when we talk about policy implications, it doesn't actually matter whether our behavioral conjecture is right or not. But what this conjecture led us to do was to hypothesize that if this is true, if this behavioral conjecture is true, we should, if it's true that a massive blood sugar shock increases demand for your product, you should expect that the food industry will have invested in working this out, right, and optimizing it, and figuring out what blood sugar shock, generates the largest, the strongest habit among my consumers, and formulating my product in a way that I can deliver that. Okay, and so this would be a costly thing to do, of course. That's where there's an economies of scale theory to this conjecture. Because it's expensive, you would expect those with the most to gain, right? Those who are producing on the largest scale to invest the most in this. So, and I want to be clear, it doesn't have to be the case that, the food industry is literally, measuring people's blood sugar when they're testing out new formulations. It could just be trial and error, right? So it could be they try different formulations, the ones that are most addictive, the ones that, that attract repeat customers the most, those are the ones that's the formulation they settle on. So that would still be consistent with our behavioral conjecture here, right? You could also think of it as sort of being driven by competition, where there are lots of food companies experimenting, and the ones that have the most addictive products are the companies that succeed and grow over the years. That would also be a mechanism that's consistent with our behavioral conjecture here. Okay, so on to the study. So continuous glucose monitoring is the cost of this is coming down, and it's becoming more and more common. So the way this works is you have this little transceiver here with a hair-thin platinum-coated probe that gets inserted under the skin. You tape it typically to your abdomen. You tape it to your skin, and it can stay there for sort of a week to 10 days. And while you're wearing it, it's measuring your blood sugar every 5 minutes, 24 hours a day. Right? And so then in your pocket, you carry one of these receivers. At any given moment, you can look at you can find a little graph of your blood sugar for the last few hours. So you learn a lot about what foods do to your blood sugar when you're wearing one of these devices. And that's for scale. That's about the size of it. You can stick that thing in your pocket. So pretty nifty little device. The Dexcom G4 is the model we used. So so we had 12 volunteers wear this device for, we asked people to wear it for at least a week, asked them to consume at least one meal at a globally branded fast food restaurant. So we did this in New Zealand, but the global brands are literally global brands. Every one of them you'd also find in Boston that our subjects were eating at in New Zealand. We had them take photo diaries. So every time they took had something to eat or drink, we had them take a photo of it. So we have time-stamped photos of every single meal event, we call them, over the course of the week. And we can match them up with the blood sugar data to get a pretty close mapping of what the meals are doing to blood sugar. Okay, so each meal event then, so we have this meal data from the photo diaries. Each meal event we code as either freshly prepared, globally branded fast food restaurant, or other off-brand processed food. Right? And so that gave us, so we had 579 meal events. So these, this is not necessarily what you'd think of as a meal. This is every time you had every photo basically in our database. So every time you had a caloric drink or something to eat and snapped a photo of it, we count that as a meal. We have 579 of those across our 12 subjects, and 24,084 blood sugar observations. Right, so it's a pooled time series data set. Just to give you an example, this is what the raw data looks like for one of our subjects. So this person chose to only have one fast food meal over the course of the week. It's right there, and you can see that immediately following it is where you see the highest blood sugar reading of the week. And that was actually true for most of our subjects. For most of our subjects, the highest blood sugar reading that we observed on them over the entire week came immediately after a fast food meal. So even in the raw data, you can sort of see what our results are going to be. So just quickly, descriptive statistics. So this is, let's see. So across our 12 subjects, so these are the average blood sugar readings, right, for the entire week for each of our 12 subjects, standard deviation. You can see there's a lot of variation in average blood sugar. Also quite a bit of variation in how much variation there is in blood sugar. And then for various reasons, different people wear these for different amounts of time. So we're going to pool these all together, but try to adjust statistically for the fact that that they have these differences from person to person. Then for our meal database, we have 330 fresh meals, 222 off-brand, and 27 globally branded fast food restaurant meals. And so just looking at this, you can see the globally branded meals are very different from the other two, right? Much higher calories, much higher carbohydrates, much higher sugar, and so on. So just to start with, yeah, on average, these meals are not similar, but we're going to control for these differences statistically when we in the end, when we look for differences in terms of blood sugar responses. Okay, so the empirical issues, I've already covered some of these. So we've got individual variation in mean and variance. We have a free feeding design, right? So this is the only instruction we told our subjects, eat whatever you want. We just ask you eat at least one fast food meal over the course of the week, right? So no structure at all to feeding patterns. There's also, let's see, we did ask subjects to take an exercise diary, because this can affect your blood sugar. But in the end, the data wasn't not all of them did it, and the data wasn't very good. So, in the end, we're not controlling for exercise. But you could think of exercise, or even potentially meals that didn't get recorded for some reason, as being unobserved shocks. Right? So this is also something that we want to, this will generate serial correlation in your residuals. This is also something that we can adjust with our choice of statistical methods. And then stationarity is something they talk about sometimes in time series data. That just means that if you have a long-term trend, this causes problems with time series data, right? It makes your residuals, if you don't address that, it makes your residuals serially correlated. This isn't an issue for us. We don't think it's an issue, and if you saw the raw data, there doesn't, you wouldn't expect there to be a long-term trend, because this is a physiological homeostatic process. Okay, so anyway, we have statistical methods to address all these things. So we use, for those of you who want to know, we use individual fixed effects, and we cluster standard errors by individual. Maybe what's more interesting is that to control for this problem with overlapping meals, we're going to, for every single meal event, we're going to control for, we're going to sort of, in our regression model, we include a dummy variable for, the fact that tells you, a dummy variable that tells you this person ate a fast food meal 25 minutes ago, right? Another dummy variable says this person ate a fast food meal, 65 minutes ago, and so on. And so we do that for, so for 42 periods after each meal, so 3.5 hours. And then there's also some interesting, there's some interesting mentions in the scientific literature about anticipatory effects. So if you know you're going to have a high glycemic meal, there's some evidence that your body might anticipate that, secrete, kind of like a Pavlovian response, right? Secrete insulin in anticipation of this and actually have your blood sugar fall before you touch the food. And so we want to control for that too. So we control for, so we do the same thing. We control for dummy variables for meal type an hour ahead of each meal. So those are meal type controls. We also generate continuous variables for a vector of nutrients on the same scale. So for 42 periods after each meal and 12 periods before each meal, I've got a variable that says this person ate a meal that had 6 grams of carbohydrate in it 25 minutes ago, right? I'd have a variable that said this person ate, a meal that had 6 grams of carbohydrate in it 65 minutes ago, and so on, right? And the nutrients we choose to control for, remember we have this, this hidden quality economics, sort of market failure framework in mind. The vector of nutrients we chose to control for are the vector of nutrients that you find on the nutrition panel on the labels on New Zealand foods, right? And it's almost identical to the US food label. There's 1 or 2 minor differences, but I forget what they are. They're not differences you would expect to have anything to do with blood sugar effects. But it's consumer information we have in mind, right? So we want to control for what the consumer knows if they were reading the label, and then sort of see if that predicts blood sugar effects sufficiently that these economic categories we come up with have no effect, no residual explanatory power. Okay, and then there's the technicalities of the time series econometrics. So we use this, I'll show you on the next slide. We use maximum likelihood ARMA estimation, it's called, where we have to choose these parameters P and Q. I'll just show you quickly the technicalities. I won't go into these, but what this means is, so the goal of time series estimation is always to eliminate serial correlation, and you want your residuals from your regression analysis to just be white noise. Right? And if there's trend, or if there's, if you looked at the raw data and it looked like there was a trend in these residuals, that means you have a serial correlation problem. But you can eliminate that with the appropriate estimation method. And so we're using this ARMA PQ method, but it requires us to have to choose P and Q. You can just think of these as smoothing parameters, right? So we're gonna estimate separate parameters. It turns out we have to estimate 10 of them in this case. In order to achieve this smoothing, right? So that we've got nothing but white noise left in our residuals. And so this is kind of important because we're, if you know anything about statistics, because we're estimating these new parameters, it actually affects our other results, right? So it's not trivial choosing the right numbers, but it turns out it doesn't really matter because our results are so strong that it just doesn't matter how much of this we do. We've chosen the specification we think is right. But it doesn't. This decision does not have an important effect on our results. So there are my results. So this is the version of the regression that does not control for nutrient content. Right? So I'm just controlling for economic categories here. Right? So the black squares are the globally branded fast food meals. The gray triangles are off-brand processed foods, and the light gray circles are freshly prepared. So times 0 here, this is when you had the meal, right? And we're controlling for 60 minutes before the meal and 3.5 hours, 210 minutes after the meal. And so the first thing that jumps out is you do seem to have this anticipatory effect. Small ones for the other two categories, big one for globally branded fast food meals. And then much bigger blood sugar shock that goes all the way out to 3.5 hours for globally branded fast food. So this is a bit surprising for us that the freshly prepared and off-brand are pretty similar. So maybe steeper slopes for the off-brand processed, but similarly sized shocks. And both much smaller and much shorter lived than these fast food meals. Okay, so that's not controlling for nutrient content. Now I'm going to show you, so the next slide I'm going to show you what happens when you control for nutrient content. So if it's true that this food label is giving the consumer full information about blood sugar effects, even the most rudimentary, full information. I mean, so the thought experiment here is the consumer actually taking this data and doing this analysis in their head in the grocery store after reading the label. It takes my computer 24 hours or more to run this, with a 4 gigahertz processor to run a single regression here. So it is asking a lot of the consumers to do this. But if it were true that the consumer could do this and they had full information was provided by this food label, then these three time series, these three meal categories should all be flat lines, right? So if the nutrient label is explaining everything, there should be nothing left in this graph. So I'm going to show you what happens to the graph now once you control for nutrients. That's it. So not flat lines, right? So this is not controlling for nutrients. That's controlling for nutrients. Right? And so we can actually. So I'll show you in a minute that we do statistical testing on this. So let's see. So I haven't shown you standard errors. Everything above. Let's see. Just rule of thumb. Everything above about 0.4 or so here. The units here are on blood glucose are in millimoles per liter. Right. This is the European standard. Everything above about 0.4. The coefficients you see represented by the dots here are statistically significantly different from 0. But that's really not the hypothesis test we want, right? We really want to say something about, more broadly about the dynamics of what's happening here. And so I'll explain that in a minute. But we can actually quantify the differences. So, going from not controlling for nutrients to controlling for nutrients, I can do things like measure the area under the curve here, which is what the nutrition physiologists typically look at when they're looking at blood sugar shocks. If I look at the area under the curve, going from, for globally branded fast foods, going from there to there, the area under the curve goes down by about 20%. So you could say the food label is explaining about 20%, predicting about 20% of this blood sugar shock you're going to get. Okay, and so we want to say something about addiction dynamics, and one of the cool things about this CGM data is that we have so much data that we actually can, do things like this, estimate the detailed level of the dynamics of the blood sugar response at a pretty precise level of detail. And so I can take a, a response like this, and I want to come up with measures that I can use to run hypothesis tests around. And so these are what we've come up with. Sort of the anticipatory effect, we're going to call craving. So C is for craving. So the area under the curve, actually I think we do it from zero back. So the area from there back is we call craving. Area under the curve we call dose. The maximum 30-minute increase in coefficients we call rate of absorption. A maximum 30-minute decrease on the backside we call withdrawal. All right, so yeah, so these are kind of dry and boring hypothesis tests, but I don't know, we make them a bit sexier by using the language of addiction, and I think that's, but I think we do it for good reason. Yeah, so you don't really need to read this table. So this is a table of p-values. Right, so every one of these numbers in these two columns is the result of a hypothesis test. The null hypothesis is specified here, and then the one on the left is not controlling for nutrients. The one on the right is controlling for nutrients. With p-values, if something's going on, the p-value is small, so you do see quite a few zeros here, and the zeros don't all go away when you control for nutrients. Okay, so the strongest results are probably for dose, right? The area under the curve after the meal, right? So we can look at, so D sub F. D sub F is, the null hypothesis is the effect of eating a freshly prepared meal is 0. Right, where are we here? See that? And so we have, it's hard to see from this angle. It's there, right? So that's the p-value. If you don't control for nutrients, that's the p-value if you do control for nutrients. So statistically significant by any reasonable measure. That's mostly true for the other types of meals too. And then down here, just for example, here we're comparing the hypothesis that the area under the curve for freshly prepared foods is the same, the null hypothesis that the freshly prepared is the same as the off-brand, right? And so, choose your significance level and decide whether or not you believe that's true, right? Fresh versus globally branded, definitely probably you would declare they're different when you don't control for nutrients, right? And at 0.05, you'd significance level, you'd say the same thing for when you control for nutrients, and so on. Anyway, plenty of. This is sort of one of the cool things we can do with this data when we do the time series econometrics right. Okay, so one other thing that one thing we were surprised by is that we didn't. If you read the literature, you see there's this. There are these reports of blood, when you eat a high glycemic meal, these reports of blood sugar falling down below baseline at some point, right? Your body overreacts to the blood sugar shock and you get this, and you may have experienced this yourself, right? That you get a blood sugar low after eating, an hour or two ago, eating a carbohydrate meal, and you get sugar cravings and you grab the ice cream from the freezer. So we were kind of expecting to see that, like we were disappointed that we didn't see a drop below baseline out here. And so one other thing we did, and I don't know that this is going to be in the paper because we really had to squeeze our data to do this. So we could extend, we're eating a lot of degrees of freedom when we do this, but we could extend beyond whatever, this 4.5-hour period for each meal. We could extend it further out to see, does something eventually happen? And so part of what our statistical method is doing here is it's actually forcing our estimates together at the endpoints, right? Because our maximum likelihood method is doing everything it can to eliminate serial correlation. It doesn't like sudden jumps, right? So it's by the time you get out to the endpoints, it's going to force these things together. So what happens now? I'm going to show you what happens when we extend this out. I hope you appreciate this. This took 24 hours for each regression. I'm going to go all the way out to 13 hours post-meal there. So I just shrunk the scale here, right? So it's the same graph, not controlling for nutrients, And there's one of the reasons we don't think this can be in the, or may not be in the paper is you can't control for nutrients at the same time as you do this, right? Can't go out to 13 hours and still control for nutrients. It's part of the reason why we chose 3.5 hours as a standard case. Okay, so there's 3.5 hours, there's 4 hours, 5 hours, 6 hours, 7, 8, 9, 10 hours, 11 hours, 12 hours, 13 hours. Okay, so we're pushing the limits of technology here given our sample size. And so I don't know whether to believe this or not, right? This is because we're squeezing our data so hard. But we do finally get, after 10 hours out here, we do finally get estimates that are down below baseline for the fast food meals. And there could be a lot more going on here. So it might be that your fast food meal doesn't really, and this is on average across the 27 fast food meals in our sample, but it could be that your blood sugar doesn't actually stay elevated for this long as a result of that meal. It could just be, for example, that as a result of this meal, you have cravings for sweet things or carbohydrate, and then out here you're eating more carbohydrate meals to keep your blood sugar this high, and because our meal dummies don't fully control for blood sugar effects, you could be seeing part of that here. But anyway, that's what we've got. Okay, so I did my best to save time for discussion here because I think it's important to talk about the implications, potential implications, and potential caveats. So there's some pretty obvious caveats that you have to add to this. If you take our results and say, oh look, the food label fails, you have to add caveats to that. So it could be that one reason that those estimates don't go to zero. It could be that it could be that there's measurement error for nutrients, right? So our photo diaries are not state-of-the-art nutrition diaries. Our sample size is small enough that so we had a technician look at the photo diaries and used nutrition software to convert them into nutrient vectors. But our sample size was small enough that if he wasn't sure about the size of a given meal or what a meal was, our sample size is small enough he could just talk to our 12 people. He could just ask them, what's that? And that happened for most subjects where there was some explanation needed. But nevertheless, there could be measurement error in terms of the nutrients, so that could be why the nutrient label doesn't explain the blood sugar effects. It could be that there are nonlinear effects of nutrients. In fact, it's probably likely there are nonlinear effects of nutrients. So, for example, it could be that there's, it takes some minimum amount of carbohydrate in your meal before you see any effect at all. And so that's right. Whereas our estimation literally assumes that every gram of carbohydrate has the marginal effect is the same for the first gram as for the 200th gram. So it could be nonlinear effects that are explaining why just because our statistical method doesn't control for nonlinearity. Or it could be their interaction effects from nutrients. And there's lots of discussion of this in the literature. If you eat the carbohydrate together with fat or with fiber or something else that speeds or slows digestion, this could have an important effect. We're not attempting to control for interaction effects of nutrients. But on the other hand, you could take any of these three caveats and say, well, wait a minute, does that really help our consumer? Right? So if my photo diaries with trained technician with nutrition software is making errors in terms of, working out what the nutrients are in these things, it's pretty unlikely that a consumer is going to do better, right? A consumer who usually doesn't have a food label, right, and doesn't have these tools that my technician has, that's probably not going to help the consumer. The same with nonlinear effects and interaction effects. It's like, I could put those in my regression and potentially explain more of this, right? Potentially explain everything, I don't know. But that's not what's on the food label, right? The food label doesn't say, oh, there's this nonlinear effect of this that's going to map into your blood sugar. Oh, there are these interaction effects. It doesn't, the food label doesn't list interaction effects. It just lists, the nutrients. So that's why we think that, yeah, it could be this is more complicated and we've missed something, but that's probably not going to help the consumer who's trying to decide what to eat. And I mentioned at the beginning that our results, that our policy implications don't depend on the addiction hypothesis. So we did start with this hypothesis that there's this behavioral conjecture that it might be blood sugar effects that get people addicted to fast foods. We provided at least weak evidence of that, right, with these measures of blood sugar dynamics. But if you don't believe that behavioral conjecture, and it is still just a conjecture, it doesn't really matter in terms of policy implications, right? Like our results still suggest that you should worry about this, right? That there's something missing from that food label, right? That there are important public health effects, and this is potentially a big market failure, whether or not this is a directly addictive property of foods. There's also discussion out there about why you can't have a food label for glycemic index or glycemic loads. And it strikes me that these arguments are often made without reference to the benefits of having a label that actually works, right? Which are potentially enormous, right? So there should at minimum be people doing research on this, and there aren't many of us. Yeah, and so measurement costs are falling. It cost me around $5,000 to do this study. Most of that was paying for the CGM device. We paid our subjects. So I have to say it wasn't. So it was very easy to get volunteers to do this study. Because if you think about it, I'm offering to let them use this $4,000 machine that they wouldn't otherwise have access to. They're getting continuous feedback about what the foods they normally eat do to their blood sugar, right? And that's information. They're going to learn something from this that's going to be with them the rest of their lives. So people were thrilled to do this, to volunteer for this. And they, even though it does, involve pricking the skin. And we did pay them a $100 grocery voucher, just to cover the cost, cover their expenses. But some of them honestly didn't even know they were getting this grocery voucher until the end. Or they had missed that, right? They would have done it anyway, obviously, because they hadn't known. And then there's the question of what the relevant unit of consumption is. So one of the things about our experimental design is that it's free feeding, right? So we're getting a snapshot of what happens to people's blood sugar in their normal everyday eating patterns. And which is potentially very different from what so I'd argue that that's what matters, right? That if you're worried about people having sustained high blood sugar or this blood sugar roller coaster, if you're worried about the physiological effects of that and the public health effects of that, it's really how people consume things that you should care about. Meaning like if there's something about the environment in the restaurant, the odors and the colors and my past associations with these things, there's something about those that induces me to order a bigger meal, that generates a higher blood sugar shock. That's the thing we should care about, right? It's the actual, if you wanted to put warning labels on restaurants, that's how you should measure them, is to actually measure what typical blood sugar shocks are for typical people eating in the restaurants. So this is a bit different from what you would normally think about with food labels, right? Where you have packaged in the store and there's a warning on the label. I mean, you could still do it at this level, but it's not necessarily the one that is most relevant to public health. Okay, and then last item there. You could ask about political feasibility. So if it's true that our behavioral conjecture we started with about blood sugar effects being addictive, if that's true, right? If blood sugar effects are sort of a fundamental determinant of consumer demand, you should expect pushback from the food industry like no pushback you've ever seen before, right? Against doing something about it, right? Against putting a label on food products that's going to warn people, oh, this is what it'll do to your blood sugar. And the global fast food business is a $600 billion industry. So approaching $1 trillion industry. Talk about a political fight. Okay, I'll stop here and take questions if you have any. Thanks. In the back there? Yeah.
They're collecting information through an app for all locations that are using the Econometrics sensors and asking them if they'd like to be included in the study, et cetera.
Yeah.
It would probably be more comprehensive, but it would also allow you to see if there's, you could do like a cohort study, something like that, to see whether or not this type of control or this type of awareness around this type of sensory reading and the process, has any relationship to outcomes for like type 1 patients or the onset of type 2 or heart disease that are on or anything like that. So I guess my general question is like, where is this going next? Where do you see it going next? People for partnerships with organizations like Amazon that are already funding this kind of research.
Yeah, thanks for that comment. So we did reach out to Dexcom before doing this study. So I mean, we thought they might be interested in, giving me a Dexcom G4, for example, to do this study. And the sales rep I was talking to, told me she talked to her boss about it, and they said no. And and I do know they're doing some research on their own, but my understanding is it's mostly organized around demonstrating the effectiveness of this device, right? And its accuracy and dependability and so forth. But thanks for your comment, and I'm going to look into that again. Yeah. So that would be a piece we'd need. Yeah. Back. So the question is, how do we deal with adjacent meals that are eaten quickly one after the other? So we just treat every one of those meals as a meal, right? So if there's a separate photograph in it, a separate time-stamped photograph for it in our meal, so the scenario you described, there would be 3 or 4 meals. And so we'd record them in our database, and we control, we estimate the nutrient content, and we control for the nutrient content. So, exactly, yeah. So, right, so we don't control for interaction effects at all. Yeah. Back there. Yeah, that's a good question. Yeah, did people change their behavior as a result of wearing these monitors? We gave them a short post-study questionnaire that asked them, and it didn't tell us too much. I mean, there were quite a few subjects that told us they were shocked, right? They were really surprised at some of the things they had found while wearing this device for the week. I don't know, but there are only 12 of them. I'm kind of tempted to chase them down again and ask that question, right? Do you eat differently now than you did before? So maybe I will. Yeah.
Were you surprised at the difference between the dose response and the off-brand fast food and the global brand fast food?
Oh, absolutely. Yeah. We expected to see. Well, let's see. So we expected to see an intermediate result, right, between the fresh and the globally branded. We thought, off-brand will be in the middle, but there wasn't, right? It was, off-brand is awfully similar to the fresh. But still, this is actually, the reason we coded our data this way is because we have this economic theory to begin with, that it's an economies of scale hypothesis, right? That the biggest companies will have optimized this the most. So we were predicting a difference. That's why we coded the data that way. So I guess in that sense, we weren't surprised, but I mean, the magnitude is shocking, right? Yeah.
Because they're making a decision in their sort of plot state, and that it's more of a behavioral response to having waited too long before they ate for something.
Yeah. Yeah, so that's a good question. So in particular, what's going on with the anticipatory effect? So you're right, it could just be that this isn't causal, right? That it's that because you have low blood sugar, then you eat the fast food. From talking to the subjects, I don't think in our study that was really what was going on, because they were told, you got to eat one fast food meal this week, and for many of them, they did just eat exactly one fast food meal during the course of the week, and they planned ahead when they were going to do it, right? They just didn't wait until it struck them. They told us that oh yeah, I decided I was going to do this, and I was, and I decided I was going to do it Wednesday, and I did it Wednesday. Does that answer your question? But yeah, we can't distinguish between those two things with our data, right? So you could call it an anticipatory effect because you're expecting a meal, or it could be that you have the meal because you had this blood sugar effect. Yeah, Norbert.
And following on that question, the participants in the study, did they typically eat fast food, or were their consumption of fast food sort of isolated to, I have to be in the study, they're going to eat fast food? And would you expect that there would be a difference in response?
Yeah, so there's a lot of variation in that. We had some subjects that eat fast food, that eat a lot of fast food, but some that I think we had a couple that hadn't eaten a fast food meal in years, and were angry with me for making them eat a fast food meal. But you definitely would expect there to be a difference. So just because people adapt. So like if I went out and started eating fast food every day, you'd expect me to have much more dramatic blood sugar effects initially. My body would then become accustomed to it, and I'd have lesser effects. Unfortunately, we only have 12 subjects, so we can't really say anything at all cross-sectionally. We ask questions like this about how often you eat fast food, but with 12 people, we can't say anything at the level of our individual fixed effects control for differences across people is the best we can do statistically. Yeah, back there. Mm-hmm. Mm-hmm. Yeah. Well, so in order for there to be a Lemons equilibrium, so first I should say there's a lot of really interesting behavioral science here, right? So I've intentionally limited myself to this rational world in which people just lack full information, right? But But of course, there's a lot more going on there that, I have other papers on that. But in order for there to be a Lemons equilibrium, Lemons market failure, you have to have one particular characteristic of the product that is unobservable, that the consumer cares about, but they can't observe it, right? So and as long as there's just one of those, you expect to see this Lemons problem, right? Well, I mean, other things go along with it, right? So that has to be, it has to, the hidden quality might also make it like less expensive to produce or something like this, or more valuable to the seller or whatever. But it's pretty simple conditions that you just need one characteristic that consumer can't observe directly, makes it a hidden quality problem, and then you expect, then that at least creates the potential for collapse of the market for high quality goods, right? So collapse of, there's no market for industrially processed low glycemic foods because the consumer has no way to distinguish one industrially processed food from another in terms of its glycemic effects. Does that answer your question? I mean, so the fast food industry does work very well in terms of observable characteristics, right? In terms of the cost efficiency of its production and distribution, in terms of literally the cost of the foods, in terms of food safety, it does very well. Things that can be observed, it does very well with. But we know from history that there have been a lot of examples of chronic diseases induced by diet that fit this Lemons equilibrium story, right? That you can't easily, the individual consumer can't observe. It's even tough for scientists to work out what's happening. So I stand behind my lemons everywhere argument. Yeah.
What would it take to scale this up? We're going from 12 people to a population large enough to maybe say a bit more.
Oh, what would it take to scale this up? Well, it didn't take that much for me to do this. It's $5,000 in a grad student, and we did. So I mean, that's my short answer. I don't think it would take much to replicate this or to take it further. To be honest, the nutrition, the research, the previous research on this that's been done by nutrition scientists hasn't taken this approach, right? They haven't taken this Lemons equilibrium idea and said, oh, this is how we should look at it. We should design our study with an eye to public policy, and I think that holds it back. It's also true that I don't think that literature knows about time series econometrics methods yet, but I hope they learn them soon. Because this is rich data, right? There's so much you can do with it. And economists use time series data all the time. So, we learn these things in grad school, but the typical biostatistician would not have much experience with these methods. Oh, one more over here. Well, yeah, no, that was the point I was trying to make, was that that's not necessarily where you want it, right? If it's not just items, but how they're consumed in practice, then you might want the label on the front door of the restaurant, right? You see what I mean?
How would that label be like 5 years ago? There's like glycemic response varies by individual. For the ingredients, for example, how different technologies do that. How would that label be measured? Like response to non-diabetic population?
Yeah. So what we know from history is that for a food label to work, it has to be simple. It has to give the consumer a binary decision, and the label. So the label itself is telling you this is a good food or a bad food, but then like where you draw the line also has to be something people care about, right? So the good food actually has to be good. So you want to. So there would definitely be like regulatory judgment required to make that decision. Like where do I draw the line? Where where do I decide this restaurant's good and that one's bad? And so, I would argue it should be something like, measure what happens to people's blood sugar after a typical meal, from their typical customers. And if it's higher, and if it's higher in their typical customer than a certain threshold, they get the bad label. But in practice, it's likely no one would actually get this label, right? So when the trans fat label came out, the industry completely reformulated, more or less, before the label became mandatory, right? So when the label was finally on the food, they all pretty much said zero trans fats. You'd almost certainly, like if you had a strong rule about you can't do this to people's blood sugar, you would see the industry almost certainly reformulate in a way that they didn't do it to people's blood sugar because they wouldn't want that label on the front door. Okay, yeah, I've gone over time, sorry. Thanks.